Okay, good afternoon, everyone. So last time we have seen MAC address, the link layer address, 48-bit, which is a 48-bit hardware address. Now this protocol is used for the data link layer. Now another function of the data link layer is the error control. I hope I'm audible.
Yes, sir.
Okay, thank you. So error control, as in, let's say we have a physical layer through which we are sending the bits, and physical layer is linked with the next layer to the physical layer is data link layer. Now error checking, error control is the job of the data link layer. That means what? Let's say I'm sending you the data, I'm the sender and you are the receiver. So let's say I'm sending you 1011. It should be reached as 1011 to your side only. It should not reach as 1010. Okay, that if that reaches as some other bits, then there is some error, and you have to detect those errors, right? And if possible, then you can either create those errors. Correct those errors, or ask for the resend. So detecting error is one of the jobs of data link layer that we are studying right now. So how does it happen? We'll just check. Do you know anything about the parity bits? Even parity, odd parity?
Yes,
So that thing is very important in error control. How to use those parity bits in error checking. We'll just have a look today. So basically, it is to detect those errors, and actually we have uh, discussed all these things. So what you have to do is you have to write this function generator. Okay. So original message that contains all the bits. Then you have a generator code which generates some code, some form, and with that form you can add some more information about that data, and then think of how that can be checked. Okay, so with the original message, some redundancy you have to add to the data. Okay, so there is original data, and you have to attach some more information about that data so that you can check whether there is a error or not. Okay, so for example, you can what you can do is you can add the parity. Let's say all the let's say there are 10 bits and you are sending the even parity. So even parity is attached as a redundant data, okay, with the code. So that becomes the actual what you can say redundancy code along with the message to you. Now one of the error checking control is Hamming code. Okay, now what happens in Hamming code is it can detect a 1-bit error. Okay, so if you are sending any number of bits, it can only detect 1-bit error. If there are 2 bits error, you have to go for another checking or another form or another method. But Hamming code helps you only with the 1-bit error, right? Now you can have 7-bit code or 8-bit code, Hamming code, or multiple. This is generally 7-bit or 8-bit code which is used. Okay, instead of in the PPT, what I'll do is I'll give you the details on the paper itself, right? So what happens in Hamming code is, let's say there is a data bit. Okay, So data number of bits are called as m. Okay, let's say there is a 4-bit data or 5-bit data. So value of m is that number of bits in the data. Okay. Okay, so now let's say data is m bits, and then you have to add some redundant bits. Okay, that is called as r bits. Okay, number of redundant bits. Now, in case of even parity, uh, only one bit can be added as a redundant bit. But in case of Hamming code, what you have to do
Sir,
is
uh, sir, could you explain about the Hamming code once more? I was just fetching the topic.
so I'm actually explaining you Hamming code only. I'm repeating everything again with the Hamming
Okay.
code. Okay, I've just started now.
Okay, sir.
Right. So a Hamming code contains of two uh, things. One part is data part where actual number of bits are there, and then you are adding some redundant part, that is r. Okay, now these are number of bits. Okay, so there is a formula of how to calculate the r is 2 raised to r should be greater than or equal to m plus r plus 1. So this formula you should uh, find out. Okay, so let us say we have 4 bit of data, 4 bits of data. Let's say the data is 1011. Okay, so what you have to do is you have to find out the number of redundant bits for the Hamming code. Okay, and this is the formula that you have to use. Now we'll check with r is equal to 1. Okay, let us see if this satisfies. 2 raised to 1, is it greater than or equal to 4 plus 1 plus 1? It is not. So this doesn't satisfy with r is equal to 1. With r is equal to 2, 4 plus 2 plus 1. So I'm just putting the values in 2 raised to r m plus r bits, because r we have taken as 2. And this also 2 raised to 2 is 4 is not greater than this one. So this is also not, this doesn't satisfy. So with r equal to 3, let's say 2 raised to 3 is equal to 4 plus r is 3 plus 1. So 2 raised to 3 is 8. It is greater than or equal to 8. So this satisfies. So for number of 4 bits, r has to be 3. So you have to add 3 redundant bits to your original data. Okay, and this is your original data, right? Now, how do you place those redundant bits? You cannot just add redundant bits. Let's say redundant bits are 3 redundant bits and 101. These 3 are redundant bits. You cannot just pad those bits. Okay, there has to be some place of each redundant bit, and we'll find out that place. Okay, so for the first redundant bit, P1, okay, that has to be placed at 2 raised to 0. Okay, we'll start with all the 3 values of r. Okay, so there are 3 bits: 0th bit, 2nd bit, and 3rd bit. Okay, so we'll try with all the values. Then P2 is 2 raised to 1. Okay, you have to find out the place of these redundant bits. Then next is 2 raised to 2. So the next bit has to go to the 4th place, not the 3rd place. Okay, If the value of R is 4, then next bit will go at 8th position. Okay, and so on. So that means what? Let us put the Hamming code directly. So total Hamming code for 4-bit data will be 7 bits, right? So I'm just writing the bit positions 7, 6, 5, 4, 3, 2, and 1. Okay. So now out of these 7 bits, which are the data bits and which are the what you can say redundant bits? Okay. So out of which for the first parity bits or redundant bit position is 2 raised to 0, that is first position. Okay, so P1 will go here. Okay, so the next bit will go at immediately next position, 2 raised to 1, the value is 2 here. So P2. Okay, but the next bit, which is P4, will go at 4th position. So that is here. Okay, and the data, which is original data, will go as it is. So the data will go as 1 0 1 1, like this. Any doubts here? So this is actually a Hamming code. We are still yet to find out the values of P1, P2, and P4. But as of now, is it clear? So first of all, we are finding out the value of number of redundant bits, okay, using this formula. Okay, given the number of data bits, you have to find out the value of R, which satisfies this formula. Once you find out that, okay, number of redundant bits, then you want to find out what are the positions of those redundant bits in the Hamming code. Okay, so it is not continuously. You have to place them as these values: 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, and so on. Okay, so in this there are only 3 bits, 3 parity bits. Now let us try to find out these values of P1, P2, and P4. Okay, so let us consider what is the binary table 0 0 0 0 0 1 0 1 0. I'm just writing all the combinations here. Okay, so these are the 7 positions here, right? Forget about the first, because these are all zeros. Let's start with actual values. Okay, 0 is not there in our group. Now, which are the positions where the P1 is 1? P1 is 1 is, we'll name these positions as M1, M2, M3, M4, and so on. Okay, so P1 is equal to, which are the positions with P1 is 1? M1, then M3. Let's not write M1. I'm just writing the positions 1, 3, then 5, and then 7, where P1 is 1. Okay, now let me find out the P2, where P2 is 1. P2 is 1 is having 2, then 3, then 6 and 7. Is it correct? For P4, what are the positions where P4 is 1? That is 4, 5, 6, 7. That is 4, 5, 6, and 7. Okay. Now what you have to do is we have to find out these values of these positions. 1 position, 2 positions, and 4th position. Okay. So how do you find out that those values? Put these values here and find out the parity. Okay. So let us try to find out the parity of these bits. 3 is 1, 5 is 1, and 7 is 1. Okay. So what is this parity? It is odd parity. So P1 becomes 1. Value of P1 is 1. For P2, P3 is 1, 6 bit is 0, 7 is 1. Now these, what is the parity of 101? There are two even number of ones, so the parity is 0. Here it is odd parity, so we are writing 1. For odd parity, 1 bit, 1 value is there. For even parity, 0 value is there. Now for the last one, P4, that is 5, 6, 7. 5, 6, 7. So it is 1, 0, 1. What is the parity of this 1, 0, 1? It is 0 again. Okay. So now these, you have got these values 1, 0, 0 of P1, P2, and P4. So actual data which is sent over the to the sender by the sender to the receiver will be 1, 0, 1. Okay. P4 is what? It is 0. P3 is 1. P2 is 0. And P1 is 1. So this is what the data you are going to send it to the receiver. Okay. Any doubts here? Okay. Now, if you are sending this data and there is some error in the any of these bits, okay, let us say this bit is changed. Okay, that means instead of 101, you are sending the data as 1110101. Okay, instead of this, right? So that means what? Some data is changed here. Okay. Now this you have received at the receiver end. Okay. Now you have to check. A receiver will check whether the data is whatever the data received is correctly received or there is some error. Okay. Now we'll check that error. Out of these, which are the data bits? Find out first which are the parity bit. This is a parity bit P1. This is a parity bit P2 and P4. These are the parity bits. Okay. And all other bits are data bits. Okay. Now you know that P1 is calculated using 1357. Okay. So what is the 3 value? What is the 5 value and 7 value? Let us put the values on the Uh, so what is the third? This is the 7, 6, 5, 4, 3, 2, 1. What is the third value? It is 1. Okay. Then what is the fifth value? It is 1. What is the seventh value? It is 1. So it is a odd parity. So value of P1 that is calculated is 1. Okay. Now for P2, you calculate the value again. Okay. Now for P2, what is that? For P2, you know that the data bits you have to check as 361, 367, because why these are 367? Because value 3 will have P2 as 1. Value 6 will have P2 as 1. Value 7 will have P2 as 1. That's why we have selected 3, 6, and 1. Okay. So what is 3, 6, and 7? All are 1. So it will have 1. Okay. Now for P4, what is the value you are getting? For P4, 5, 6, 7. Okay. For what are the 5, 6, 7? Again, these are 1, 1, 1. Okay. So any doubts, guys? Again, it is a odd parity. Okay. So what is the value you are getting here? 1, 1, 1. And that means a seventh bit is changed. What is the value here for 7? The seventh bit is changed. Okay, there was an error in 7th bit. So what you can do is either you can convert that bit, or you can ask the sender to resend the data. Okay, so there are two options of correcting the data. One is, if it is 1 bit error, then you can change the data. If you are not sure, let's say instead of 1 bit, there are 2 or 3 bits changed, then what you can do is you can ask the sender to resend the data. Okay, so that is how you check. Now this is not whatever the values you are getting, these are not the values which are matching with the received parity bits. Okay, so this is the calculated parity bits, and these are the received parity bits. Okay, so when this doesn't match, you have to ask for resend, or you have to find out which value was changed. Okay, so this is the Hamming code, a complete Hamming code. Okay, which only works with the 1 bit error. Any doubts, guys?
Sir,
Yes.
so how did we come to know that the seventh bit is changed?
How do we come to know that? What is the question?
Sir, how did you know the seventh bit is changed?
See, the calculated parity P1, P2, and P4, the complete value is 1. So what you have to do is you have to put these values as P1, P2, and P4. Okay, so that way, what is the decimal conversion of this binary?
7.
7. So that gives you the 7th bit. There was a problem with the 7th. So what you have to do is you have to work with all this binary table that you have studied up till now, and these P1, P2, P4, why you have to choose these data bits or the position bits in this calculation, because P1 will be 1 for only M1, M3, M5 and M7. Okay, that's why P1 is calculated as this one. Okay, and the bit position 1, that is P1 itself. Okay, and that you have to calculate with along with the 3, 5, 7. 3, 5 and 7. Okay, so if we work with even parity, that means what? You have to make the parity as even. Now, right now, what is this parity? With 3, 5 and 7, 3, 5 and 7, it is odd. To make it even, what should be the value of P1?
Sir, 1.
It should be 1. So that's why we have got the P1 value as 1. For P2, now as you know that where are the P2 values are 1, 2, then 3, and then 6 and 7, right? So now you want to find out P2 value, the second position. Okay, so what is the value of 3, 6, 7? 3, 6 and 7, 1, 0, 1, 1, 0, 1. Okay, so now it is odd parity or even parity?
Even
Even parity. So you don't have to change because you have already got the even parity. So you don't change the P2. Okay, if you make P2 as 0, then the complete value will be even parity. Okay, that's why the value of P2 is 0. If you make P2 as 1, then what will happen? The complete uh, parity of complete data here becomes odd, but we are working on even parity. So that's why we are not making it as 1, we are making it as 0. Similarly, P4. For P4, which are the positions having 1? 4, 5, 6, 7. Okay, out of which fourth bit you want to find out. Okay, so let us put the values of 5, 6, 7. 5, 6, 7, 1, 0, 1. Okay, it is a again even parity. So if you put the value of P4 as 0, the complete parity will be again even. So that's why P4 value is 0. And then we are putting the these values as P1 value we have put as 1. Okay, P2 value we have put as 0. This is the original data, 1011. Okay, and this one P4 is again 0. This is the fourth position, and then this is the again original data, 101. Got this? Any doubts?
Sir, if possible, sir, you can take some next new data and explain the concepts quickly again.
Okay. Let me
Yes.
take the other example here.
Yes.
Let me take the 1101 data. Okay. Now I have to put that in a Hamming code. Uh, 7, 6, 5, 4, 3, 2, 1. Okay. Out of which P1 has to be found out. P2 has to be found out. This is the data bit. Okay, so we are putting this as 1. Then P4 has to be found out. Okay, this is the next data bit. This is the next data bit. Okay, now these values has to be found out. P1, P2, P4. Any doubt here? Now for P1, which are the positions? 1, 3, 5, 7. Okay, so 3, 5, 6, and 7. So what are the values of P1, 3, 5, 7? This you have to find out. P1. Value of 3 is 1. Value of 5 is 0. Value of 7 is 1. Okay, so what should be the value of P1?
0.
0. So P1 becomes 0. Okay, now let us try to find out P2. For P2, what are the numbers that we have to consider?
2, 3, 6, 7.
2, 3, 6, and 7. Is it correct, all of you? Two, 3, 6, 7. That is correct. Now let us put the values. P2, second position, P2 is there. That's what we have to find out. Value of 3 is 1. Value of 6 is 1. Value of 7th bit is 1. Right? So what should be the P2 value?
1.
1. Because to make this even parity, if you put this P1 value, P2 value 1, then only the complete data will become even parity. Okay, so value of P2 will be 1 here. For value of P3, what are the numbers? 4, 5,
4, 5, 6.
7. Okay, so P4, 5 is 0, 6 is 1, 7th is also 1. So what should be the parity here? It's already even, so P4 value should be 0. Any doubts here? And now what you have to do is, before sending the data, you just put these values. P1 value is 0, P2 value is 1, and P4 value is 0. So you have to send this data to the receiver. Now at the receiver, what will happen is, you have got these bits. Again, you will calculate the same thing. Okay, it will discard these bits, and the receiver will recalculate P1, P2, P4. And if the bits are not changed, you'll get the same values. And if you get the same values as P1, P2, P4, then the what you can say, then there is no error in the data. Got the point here? And you have to remember this formula. How do you come to know that R is 3? Or let us say M is 5. Let us calculate for M is equal to 5. That means if the data is 5 bits. Okay. So for 5 bits, obviously these 3 values will not match. Okay. So let me put the value as 3, R as 3. 2 raised to R greater than equal to M plus R plus 1. Okay. So what is the value of R we are putting? Let's say 3. So it doesn't match here. 5 plus 3 plus 1. This is 8, and this is 8 plus 1, 9. 8 is not greater than 9, so this doesn't match. Okay, for 5, R is equal to 4. So let us have 2 raised to 4 is greater than equal to 5 plus 4 plus 1. So 5 plus 4 plus 1 is 10, and this is 16, which is greater than or equal to 10. So this matches. So in case of m is equal to 5, R has to be 4. Or if you consider m as 6, then also R is equal to 4. You just put the values here as m is instead of 5, you just put the value as 6. This matches. So for even for 6 bits of data, the redundant bits or parity bits has to be number of 4 bits are 4. Any doubts? Now, actually, see, Hamming code is error detection of a single bit. Now the problem with Hamming code is if there are multiple bits changed, then you can't detect what's the problem is. Let's say there are 2 bits flipped. So what will happen is the parity will be calculated as correct parity. Okay, so in that case, if the multiple bits are flipped or changed, or there is a multiple bit error, then Hamming code doesn't work. Okay, for that you'll have to go for something like BCH code. This is the algorithm proposed by Mr. Bose and Mr. Chaudhary. So BCH code is usually used for multiple bit error checking. But better way to, once you have detected the error, you ask the sender to resend the data. That is the better way to handle the error connection. Okay. Another way is CRC. I don't know if I can finish this CRC code here, but let's see how it goes. So CRC is cyclic redundancy check. Okay. Now, let me go to the. So if you can, if you want, you can just go through the PPT. Everything is mentioned over here in a PPT form. Okay. The same calculation is given with more number of data bits and more number of parity bits. If you want, we can see this example also. Let us use this example. What is the number of data bits here? 7 bits of data. So for 7 bits of data, what will be the value of R?
4.
It should be 4 only, because we have already seen this here. For 5, 6, even this calculation will be okay for 7, because if you just put the 7 value here, 7 plus 4 plus 1, that goes 12. So which satisfies this equation. So 4 is the value of redundant bits in case of 7 bit of data. So let us say this is the these are the data bits. Now the only addition to this is P1, then P2, then P4, and then it will have P8 or R8. Now in this they have considered as R1, R2, R4, and R8. Okay. Now, for R1, which are the values you are going to, which are the positions you are going to consider? This value, this value, this value. Wherever the last uh, bit is 1, you consider those positions. Okay. So what we are doing here is we are directly writing the data as it is in the Hamming code 100. Then we have a parity bit, then remaining 110. Then we have a parity bit, and remaining 1 is kept over here. And then we have two parity bits, P2 and P1. Okay, or R2 and R1. So how do you calculate the R1? Let us consider this bit, all alternate bits. Okay, 1 0 1 0. So this is a odd parity. So value of R1 is 1. Okay, that's why you are putting R1 as 1. Okay, now forget about P1. Here it is given as R1. So in multiple books, you'll find different nomenclature. So the concept is same. For R2, you should be consider the positions 3, 6, 7, 10, and 11. Okay. Now, why 10 and 11 we are checking here? Because with the 4 parity bits, you have to find out the table of 4-bit table. So which will have 16 bits, 16 values, 0, 0, 1, 0, 0, 0, 1, 1, and so on. Okay. So this is how R2 is calculated. Let us put the values of M3, 6, 7, 10, and 11. What is the value of 3? It is 1. Then position 6, it is 1. Position 7 is also 1. Position 10 is 0. Position 11 is 1. What is the total parity of these this group? It is even parity, so it is, we are putting it, the value of R2 is 0. You just go through this example and just check if there is any problem. And when you put these values in the code itself directly, the final code is this one. So that will have 11 bits, 7 data bits, and 4 parity bits or redundant bits. So did you get why some people are using R1, R2? Because they are calling it as redundant bits. Some people are calling it as P1, P2 because they are calling it as parity bits. So any which ways you are calculating the same thing. And this is the final code. And the next lab, what you have to do is you have to calculate whole thing. So this will be the input. You'll have to find out the number of bits you have to calculate. Once you have found out this, then you have to do this calculation. Okay. And then you have to print this Hamming code. So that's how you write the program in C, C++, Java. I think you are studying Java also. So you can use any language, programming language. and do this, write the program for this calculation. You can consider 4-bit data, you can consider any length bit data. And please let me know if you have any doubts. Now I can't explain CRC because it's last 10 minutes. Can't explain CRC now. So here is the example. Let's say 5th bit is changed. How do you check how the receiver will come to know that there is a problem with the changed data? So when you calculate R1, R2 again, R4 and R8, then you'll come to know, there is some problem. It doesn't match with the original data, original parity bit and the next parity bit. And when you put the values of R8, R4, R2 and R1, calculated R1, then you'll come to know that what is the group, what is the decimal value of this? It is 101. Just 101 is 5. So that means 5th bit is changed. For calculating the new set of R8, R4 and all these things, you have to just recalculate these things. And calculating R1, R2, you again have to follow the same rule. So what you do is you consider any data. Now you know the technique how to calculate those parity bits or redundant bits, and then you can flip any bit in the data, any position bit, and just try to find out whether you can find out which bit was flipped or which bit error is received. And this is the way to calculate which bit was having the problem. Now, while you are writing the program for this calculation, okay, how will you find out the number of redundant bits? You have to keep checking the correct value of R which satisfies this formula. So you have to write a function for this, calculating the value of this function or this formula, and that returns whether R is correctly assumed or not. If this condition is satisfied for selected value of R and M, then you can return that the value of R is chosen. So actually, the next topic was cyclic redundancy check, but it won't be covered right now. We'll cover it in the next lecture.